Fiber Optics 101, NCAB has met the standards and requirements of the registered continuing education program. Upon completion of the program, you'll be able to, in a couple, 3 days, you'll be able to get a link on our website and download the exam, take the exam, and then if you receive a 70% score, they'll give you one continuing education credit, which might be valuable for if you're trying to maintain your PE license. If you have any questions about how to do this, just email NCAB or myself, and then we'll explain how to do that. The purpose statement, you can kind of read this yourself, and what we're going to be discussing is what is an optical fiber, how does it work, and why do we use it? We're going to talk about some of the parameters that people use in order to design a fiber optic system, and some of the limitations on the fiber itself. How does this thing work? How does it conduct this electromagnetic wave down the length of the optical fiber? A little bit of history. The optical fiber communications more or less started in 1966 when Charles Cow and George Hockham at Standard Telephone demonstrated that you could transmit information from a laser through an optical fiber and get that data on the other end. Unfortunately, the fiber was so poor they could only do a few meters. Charles Cow said that if you can continue to advance in making the optical fiber clear and reach something less than 20 dB per kilometer, we think this is a viable transmission medium. And in 1970, a group of 3 scientists at Corning Glassworks made the first fiber, which had less than 20 dB per kilometer, and it's been going gangbusters ever since. Let's see. Your learning objectives, again, you can read this. We're going to go through most of the important values or parameters for optical fiber, some of the advantages of using it, what some of the terms mean, how they're defined, and then we're going to talk a little bit about a couple of the fiber types that have come out that are specialized, you might say, for for communications. This learning hub, this Fiber Optics 101, is part of a continuing education series from NCAB. Our boss has kind of made a decision that we're going to take some of our learning. Him and I have both been in the business a long time, and try to share that with our customers and people who are interested for their own use. Please ask questions during the seminar or the webinar. Mike I've got a team of excellent people ready to answer those questions for you in the chat or the Q&A portion of the WebEx. We're only going to talk about technical questions, and we're not going to be discussing anything with regard to commercial business with NCAB. That's not the purpose of this seminar. It's just for education purposes. Well, let's get started. What is fiber optics? When we think of fiber optics, we really think about the entire technology surrounding transmitting electromagnetic waves down this hair-like optical fiber. You can see from the slide that the optical fiber is able to capture and retain the light wave as it travels along the bends and twists of the fiber. We're going to try to explain how that happens, why that happens. And what's amazing about optical fiber is that they have created a silica fused fiber that is so clear that if the oceans were made out of it, you could see to the very bottom of the deepest part. It's pretty amazing how clear and good this transmission medium is. The way the technology, the way this is able to work is a concept called total internal reflection. And this this is, let's see, how do I explain this? Scientists, they have learned to modify the material in the core and the cladding such that they can contain and guide this optical fiber, this optical ray, or this electromagnetic wave all the way down through the length of the fiber. They've done that, or modify the index of refraction. They've done that using, like germanium oxide, boron oxide, and other dopants that have allowed them to control that. And TIR, or total internal reflection, it really means that when the light enters the fiber, the fiber is able to contain that and control that such that it can go all the way to the end without losses or attenuation in the optical fiber, assuming no external uh, uh, foreign bodies or whatever is in the fiber. So why do we use it? Well, simply put, it's an incredible medium for transmitting information. An optical fiber or electromagnetic wave travels in the core of the fiber at something like 200 million meters per second. That's 5 times around the Earth. And we are just beginning to tap the potential of optical fiber. As you can see, where we're at today, or maybe this is an old slide or whatever, but this one optical fiber cable can do the same amount of information carrying as this group of Cat6 copper cables over here. And there's many other advantages, but you can see right now that if you've got a duct bank that's full of copper cable, both either telephone or data, that you can pull all that out and put in something that's much less, much smaller in area. The other instance is distance. We can go much further with our data. We can go 100 kilometers with optical fiber, and we can't go anywhere near that with copper cable. And at the end of the 100 kilometers, we're going to have a significant data amount on the other end. So another important issue is EMI resistance, or immune to EMI. Fibers are insulators. No electrical current flows through them. In addition, the electromagnetic wave inside the fiber is trapped, so none of the signal leaks out during transmission. The ability of the optical fiber to isolate itself from the environment allows us to pack numerous fibers inside the cable with no crosstalk. Also, it's more secure. Fibers do not radiate energy. The energy within them is difficult to detect. The fiber would have to be physically modified or tapped to obtain the signal. How does it work? Well, you can see some of the terms there. You've got an acceptance cone, which shows you how much light can enter the core. We're going to get in, talk about what those angles are and how do we achieve those angles or get those angles. We've talked about controlling the index of refraction in the core and the cladding. So those simple, controlling the index of refraction in the core and the cladding are really how we control or guide this this light wave down the optical fiber. The refractive index, which is an important term for fiber, is really a ratio. It's a ratio of the speed of light in a vacuum to the speed of light in a medium. And this is important because I've got a slide to demonstrate this. This is important because we need to be able to, as the light wave hits the boundary between the core and the cladding, we're able to bend that or make sure that it refracts or reflects back into the fiber itself. In 1621, an astronomer, physicist named Willibrord Snell discovered an exact relationship between two angles between two refractive indexes with respect to normal. We draw a line here perpendicular to the boundaries of the core and cladding, and that's what they call a normal line. The important thing to remember here is the light ray will bend towards normal when going from a medium with a smaller index of refraction, and in this case it would be the cladding, to a larger index of refraction, which would be the core. Oh boy, this is the wrong presentation, folks. Is it? No. Yeah, this is the wrong one. Oh shoot. Anyway, what I had, I apologize. I thought I had this right. What I wanted to show here with Snell's law was an analogy of a four-wheel drive Jeep. Okay, going from a muddy environment to a pavement. If you can imagine this Jeep going through this core of mud, if you will, towards the cladding or what we'll call the pavement, the nice smooth pavement, you'll see with both tires rotating, you'll see that when it gets to the pavement, the left tire is going to grab first and turn it towards the towards away from normal. Okay, away from normal, and that's what we mean by index of refraction. Okay, so this is the incident angle here, the angle of incidence, the light coming into the fiber, and it's going to be refracted, and in this case, it's going to an angle of incidence here, it's going to refract and get out of the core. Here it's going to refract, got an angle of incidence such that the angle allows this ray of light to travel along the boundary of the optical fiber. Now that's what we call the critical angle. This is very important to further analysis of the fiber. Okay, and then the next is the angle of incidence when it's greater than when the light wave angle is greater than the angle of incidence, then it's going to be reflected back into the core. So, let's see. Yeah, I just have to continue on here. Let's see. Okay, acceptance angle and numerical aperture. Now these are very, very similar and they depend on each other. The acceptance angle is a cone of light, you might say, or the angle such that this is the maximum angle, but this is actually the angle of incidence here. Okay, this is the maximum angle in which the light can enter the core and stay trapped in the core and transmit all the way down to the other end. Okay, this is with regard to the fiber axis, it's the maximum angle both on both sides of the core, and this forms a cone. You could imagine a cone on the outside of the fiber, and this is at degrees. How many degrees do we have that these light waves can enter into the core? The numerical aperture is a value based on, so the acceptance angle is basically 2x of the critical angle. If the critical angle is 30 degrees or 20 degrees or whatever it is, the acceptance cone or the angle is going to be 2x that. Okay, the fiber, the numerical aperture is just a value of its ability to collect and confine the ray inside. It's very important because it determines how strongly a fiber guides the light and how resistant it is to bending-induced losses. There's a formula. It's a sign of the differences between the core and the cladding, square root of that. I apologize, I didn't put it on here, but the math is available to show you how to do that. So each one's important and each one relates to each other. Come on, there we go. Okay, what are the basic fiber types? We've got step index multimode, we've got graded index multimode, and we've got single mode. We don't show the step index multimode here because it's not used very much anymore. We primarily use the graded index multimode. The step index multimode, it's basically got a core of one index of refraction and a cladding of a different index of refraction, much like a single mode fiber. And it allows, because of the core size, it allows a lot of different light rays or modes going down the length of the fiber. The graded index multimode is, is where the refractive index of the core is greater through the axis of the fiber, and it gradually decreases from the center to the boundary between the core and the cladding. This will decrease, this will speed up the light rays or the waves of light as it moves from the core to the boundary of the core cladding, so that these waves, it goes, it starts here, slows down, gets to the core. I mean, it slows down in the core. If it goes like this, it tries to escape, and it keeps turning back towards the center. And as we're refracting that core, refracting that wave such that it's going to be turned towards the center of the fiber, and all the way down the length of the fiber. I know I didn't explain that very well, but I had a slide here showing that. I don't know what I did with that. Electromagnetic spectrum. The electromagnetic spectrum is all around us. It's generated primarily from the sun. The electromagnetic waves are, the visible light, radio waves, infrared, X-rays. What it is it's a ray. it's a ray of light having an electrical and a magnetic property that propagates down or transversely to the from the beginning to the end of the fiber. I don't have a picture of that wave, but I'll show you that when we get to our PMD distortion. The optical wavelengths in the wavelengths that we use for optical fiber communication are typically in the infrared, from about 700 to 16, we'll say. The 850, those were in the early days, all of our communication was handled by 850 multimode fiber, 5125 fiber. It's relatively shortwave, lower capacity, lower bandwidth fiber, but it's the only equipment that we had at the time. We didn't have the lasers, we didn't have the detectors in order to transmit at the 1310 or 1300 wavelength. The 1300 was a window in which we had the lowest attenuation at the time, and it's now being used almost entirely for single mode fiber, that and 1550. The fiber to the home, fiber to the home is generally around 1490 nanometers, and the long wave, some of the specialty fibers for dense wave division multiplexing and other high density communications are in the 1550 and in some cases up to 1625 communication. The electromagnetic the properties of an electromagnetic signal, okay, they have no mass. They can travel in a vacuum, and they don't require a material medium for transmission. They propagate by varying electrical and magnetic fields, such that the two fields are at right angles to each other, and in the direction of the in the direction of the wave or down the length of the fiber. As you can see here, we define wavelength, or the crests of the electromagnetic wave. The distance between one crest and the other crest is a wavelength. The distance for frequency, we say that how many of these crests can go by in a period of 1 second, and these are normally called hertz. And then how many wavelengths or how many crests can we go by in 1 second is a hertz or a frequency. Attenuation or performance factors. We're going to be talking about attenuation and dispersion. Attenuation is obviously the loss in signal strength. How much power did we lose down the length of the fiber? And it's expressed in decibels. There's intrinsic, what happens, as part of the manufacturing process. Extrinsic, which is usually something that the environment's done to the fiber, whether it's cabling or whatever, that causes attenuation. And what we're trying to do is minimize this so that the maximum amount of power from the laser to the detector, you want to reduce the amount of loss you have between the laser pulse and the detector, so you can maintain that pulse or that information all the way down the fiber. I've got a slide that shows that. Dispersion is the spreading of the light pulse. Okay. Um, Dispersion is a name that's given to the property of a variation with wavelength. Different wavelengths through the fiber travel at different speeds. And as these waves reach the end of the fiber, we'll find that what it did was cause that pulse to expand, to broaden. Um, and there's three different types. There's modal, which really affects mainly the multimode uh, fibers, the chromatic, and the polarization mode dispersion. Intrinsic attenuation. It's also called material absorption. It's caused by the conversion of heat to heat by molecules in the glass. Primary absorbers are the residual ion, OH ions, water, or dopants, the metals and so forth, in the glass, which are used to modify the index of refraction. The molecules move randomly through the glass in the molten state, and as the liquid cools, the liquid glass cools, the movement ceases, and upon reaching the solid state condition, the random molecular locations are frozen within the glass. This results in localized variations in density and refractive index. A beam of light passing through this structure will have some of its energy scattered by these objects, and this is called Rayleigh scattering. If the scattered light maintains an angle that supports forward travel in the core, then no attenuation occurs. Some portion of the light will travel back towards the source. This is called backscatter. And this is what an OTDR uses to test the optical fiber. And get with it here. Intrinsic attenuation, as I said earlier, it's the absorption of energy as it meets these particles or these molecules inside the optical fiber, and it turns to heat. And Rayleigh scattering, like I said, it'll hit some sort of a metallic ion or an OH ion, and it scatters. And you can see it scatters in all directions. Some of the scattered light moves out of the cladding and is lost. Some moves back, some moves towards the core. Obviously, we're trying to reduce these imperfections in the fiber, which reduces some of this Rayleigh scattering. Macrobending. Macrobending of an optical fiber is the attenuation associated with bending the fiber. Energy or light can leak out of the fiber when the fiber is bent. As the bend becomes more acute, more light leaks out. Typically, macro bends are bends large enough to be seen by the human eye. There's the micro bending. Micro bending is a small scale bend or perturbation in the fiber. It's usually a bend less than a millimeter in radius, and it occurs often when pressure is exerted on the fiber from an external source. And also whenever, other cable components within the cable press on the optical fiber. It can be reversible. We can rewind the cable or rewind the tube. And a lot of times some of these bends will disappear and attenuation will go down. We just have to work with it so that the fibers move to a place of relaxation or least stress. And sometimes these attenuation problems will either diminish or go away. So what we're talking about performance. Missed something here? Did I? Let's see. Did I talk about? Because okay, there's dispersion. All right, got it. Okay, here's just a graph showing what happens if we lose attenuation within the fiber. If we lose 3 dB of performance or power, we're down 50% of the power in the cable. So everything we can do for packaging that fiber, for reducing the amount of stress that fiber sees, is optimum for reducing the amount of power loss in the fiber. Dispersion. Okay, dispersion. Okay, I'm okay. Never mind. Dispersion, like I may have said earlier, is a name given to the property of the loss. Okay, dispersion is a name given to the property of velocity variation with wavelength. Okay, I want to try to, so that each of these pulses, okay, a light pulse from a laser, it has a certain spectral width, and you can see different colors of different wavelengths, and each one of those wavelengths um, is traveling at a different speed down the optical fiber. And that's because you get a index of refraction variance by wavelength. I don't know if I explained that very well, but if I've got a spectral width of a laser that's, say, 4 or 5 nanometers or 4 or 5 wavelengths, and each one of those wavelengths are going to go down to the end of the fiber and arrive at the end of the fiber at slightly different times. And that's chromatic dispersion. Modal dispersion is where these modes of light traveling down the length of the fiber in different paths will arrive at the end of the fiber at a slightly different time. The modes that take a straight path down the center of the fiber, or the fibers that, or the modes that travel a zigzag pattern down the length of the fiber. Each one of those started out at the same place, but they got to the end at a little bit different times because of the distance that each one traveled down the length of the fiber. In a step index fiber, that's a problem. We have a lot of modal dispersion in a step index. What we did to correct that is we came up with a graded index multimode. And what this does is it basically speeds up the fiber as it tries to escape out the cladding of the fiber. So this wave moves down the length of the fiber in a sinusoidal pattern. Okay, in other words, it's going faster, it goes up, and it finally bent down towards when it hits the cladding, it's bent down towards the core and all the way down to the end of the fiber. It goes down through this sinusoidal wave all the way down the fiber. And we have polarization mode dispersion. And I think that's where I have a slide of the actual electromagnetic wave, which shows that under certain conditions, the installed fiber may be under stress, and that shows how that looks. Okay, like I said earlier, modal dispersion. Okay, we've got these individual paths going down the length of the fiber, and they arrive at different speeds, which broadens this pulse. Okay, and same way with chromatic dispersion, they've got different colors travel at different speeds down the fiber, and they will tend to overlap and also broaden out the pulse and cause, what this does is it causes errors. In other words, it's ones and zeros. We're going to transmit a 1 or a 0 down in each of these pulse, and if it gets too close together, if these frequencies if these wavelengths are too close together here, you're not going to be able to tell the difference, and they're going to run into each other, and it's going to cause an error. I think I've already explained this. It's the phenomenon of a pulse with different colors of light traveling at different speeds through the fiber. And that's because, like I said earlier, that's because that each of these wavelengths travel, the index of refraction for each of these wavelengths vary. And so it's going to change the speed of each one of these wavelengths as it goes down the optical fiber. Okay, polarization mode dispersion. It's primarily in single mode only, and it's comprised of these electromagnetic waves, like I show here. We've got an electrical component, we've got a magnetic component, and they typically go down the fiber together or joined transversely along the fiber, and they wind up at the other end at the same place. Well, if we have certain conditions, maybe fiber geometry, uh, maybe stresses on the fiber, ovality, whatever the case may be, these two components will travel at different speeds down the fiber, and they wind up distorting or dispersing or broadening that pulse as well. It's a fairly new phenomenon that we've starting to look at because of the increased speeds and rates that we're transmitting data down the optical fiber. Okay, here's a graph of here's an example or a picture of the dispersion we're talking about. Here's the theoretical impulse, a square pulse going down the fiber. A laser triggers on and you get a pulse. Theoretically, it's nice and square and a nice square wave traveling down the fiber. In theory, in actuality, it's slightly rounded and going down the optical fiber. You can see there's a space between the pulses. One, and here's where with some pulse broadening, but not enough to where we can't distinguish ones and zeros. And if we've got too much pulse broadening, it all kind of runs together and we've got an error and we can't determine at the other end what we sent down the fiber. Attenuation. Attenuation, I think we've discussed this. Attenuation is really the loss of signal strength going down the optical fiber. Some of it's affected by manufacturing. Some of it's affected by the optical fiber itself, and it's some of the problems they've had during the manufacturing. When we get an optical fiber at the plant or for production, it's generally comes in or it's specified to come in at 0.35 dB per kilometer and at 1310 and 0.25 dB per kilometer at 1550. Typically, if you're doing something, if you're putting it in a cable correctly and you're not stressing the fiber, you're typically going to get a value as cabled of about 0.34 and about 2.20 at 1310 and 1550 respectively. For multi-mode, it's a little bit higher, obviously, because of the 850 attenuation or the Rayleigh scattering. And at 850, it's typically 3.5 dB per kilometer and 1.5 dB per kilometer. The best practice, we don't make enough. We honestly don't process enough at this of multi-mode fiber to really have a huge database of values to tell you. But in generally speaking, it's a little bit lower than what we get from Corning, maybe 3.3, 3.2, somewhere in that territory, and 1.2, 1.3, something like that. It's typically a little better than what we actually, or what the specified values are. Dispersion, the spreading of signal pulses. It's overwhelmingly from Corning, from the fiber manufacturing process. It's specified by the fiber supplier. In other words, he's telling us he's made the fiber. Here's what the dispersion is in picoseconds per nanometer kilometer. And there's not much we can do about that. With regard to dispersion, maybe polarization mode dispersion, we have some impact on if we've induced stress or either during cabling or during the installation. But generally speaking, the dispersion is going to be what the fiber manufacturer gave us. A couple of new fiber types that I'd like to talk about is we've got a non-zero dispersion shifted fiber, and probably some of you have heard about this. It's really for dense wave division multiplexing. It's where they send numerous, they can modulate lasers at close to 1550, and they can do multiple lasers at 1550, and they have to be careful about dispersion in the 1550 area. If it doesn't have dispersion in that area, what we have is that we have something called four-wave mixing. In other words, four of these waves can mix and produce a new wavelength, which really results in extra noise and degrades the performance. So if we add a little bit of dispersion in that wavelength or in that area, what we do is we ensure that each wavelength travels at a different speed, minimizing that possibility of interaction. So we've shifted zero dispersion to a wavelength by using a different core refractive index profile. I hope I somewhat explained this, but this is fairly popular in high data area, high communications areas in cities and so forth, where you take I mean, like I said earlier, this optical fiber has huge capacity. What we're trying to do is figure out how do we utilize all the capacity in this optical fiber. So one of the ways is they've taken multiple lasers and staggered the wavelength of, or the carrier of those lasers, and they transmit them at virtually the same time. And now they've got to keep them separated all the way down the length of the fiber. And the way they do that is by adding a little bit of dispersion, like I tried to say earlier. And the next thing is it's what they call a single mode fiber ultra low loss, or G64 G654 fiber. And this has a zero dispersion wavelength around 1300 with loss minimized, and the cutoff wavelength shifted at around 1550. This fiber was actually first introduced in 1988. It's really for very long distance communications, and such as transoceanic submarine cables. It's because of the large effective area, it reduces polarization mode dispersion. And Corning tells us that we're going to start seeing more of this type of fiber, and it's because it's going to be used for more and more. Right now we're going through a boom in fiber optic communication. As most of you know, we're developing rural broadband to get fiber optic communication to the users in the rural areas. This data has to start somewhere, and the amount of data that we're starting to absorb throughout the world actually requires that we have a better way, or a faster way, of getting that data to the end user. And these are one of the steps that the manufacturer is using to do that. And what this slide is just to show you the differences in the size of the optical fiber. You can see how it's very close to the size of a human hair. It just amazes me that we're able to send this much information down this glass fiber that's only roughly 8 microns in diameter. And finally, that's it.